Welcome everybody. So last year I did a poster presentation about my smartref library to emulate smart references using C++. Since then I've been continuously developing my library, and today I would like to share the results that I found with you. So what I will talk about, first I'd like to motivate why I started working on this library, and I will try to convince you that we actually need such a language facility. Then I will demonstrate how to do it currently with my library, after which I will discuss the design of my library, and then I will conclude by giving a conclusion. Questions, please keep them for after the presentation to keep it within the 30 minutes. Okay, so as a motivation, I would like to discuss two examples. The first one is the strong typedefs. So let's say we have here a piece of code in which we have two types, a file name and a URL. So we want to make everything type safe, so we create two special types for them. In fact, they are just strings. So what we can do with them, we have defined two read functions that dispatches on the type. So one read function for the file name and one read function for the URL. So then we can use it, because it's just a string, we can use cout to print it on the screen, and we can call the read function, and then it will automatically pick the correct function. But in fact, this does not work because we are using aliases. Those types are in fact the same. They're both strings. So those two functions that are defined there, they are not really overloads. So this won't compile. So how we could fix this is by coming up with a kind of imaginary type. Let's call it strong typedef, which in fact makes a unique type based on some type. So in this case, the T would be string. And we also give it a tag to make it really distinct, because otherwise it would still be the same type. So how we could use this, so instead of aliasing to string, we now alias to this strong typedef, and then we create two unique types, and then this would work. So this is the example for strong typedefs. So with smart references, we should be able to create this. Another example is proxies. So let's say we have our data model, a map of a string to some very big data set. In this case, a vector. So you can imagine of 1 million of those mappings to very big objects, like 1 gigabyte each. If we have this data model in memory, that will never fit. So that's why we use a proxy to lazily load this into memory. So as soon as it's being accessed, it should load the data from disk, and then you can use it as if it's a vector. At the same time, we have a small model in which the value is just an array, so it's very small, and this data model will fit perfectly in memory. And then we have a generic function. It doesn't really matter what this function does. The point is that it's generic. It should work on both data models. So in this case, given a key, this function averages the data corresponding to that key. And you can see that it should work for both the small data model and the large data model. So this proxy should mimic the interface of the underlying data type. Now again, how we can do this by defining some kind of magical proxy type. Later we will show how we can in fact create such a type. And then we can create a proxy of a vector, of double, but also of int, a proxy of a map, and even user-defined types. So what is a smart reference? You can also compare it with a smart pointer. So a smart pointer tries to mimic the interface that you would get if you use a pointer, but it add some additional behavior to it. So if you use it, you can dereference it, you can use the arrow operator, and yeah, you can implement this in C++ because we can overload the arrow operator and the dereference operator. For smart references, you would you would need a similar facility in order to make this work. So, for example, the operator dot, yeah, that could make this work. But yeah, the problem is we don't have this operator, so this would not compile. So, yeah, smart references. There's also something else. The unified call syntax, which means if I have a free function defined, I need to call it with a free function call syntax. But it would be nicer if we can have an object and call the free function using member function syntax. And yeah, I can give an example. So given a vector of some numbers, we have a set of operations. We can write it in two ways, either with a free function syntax or the member function syntax. And I would argue that the second notation is much easier to read because yeah, it reads in a linear fashion. And the first option, you are constantly going back and forth. So there are also several proposals to do this, but yeah, they are problematic, so that's why they haven't been accepted so far. But it turns out that the library that I'm working on also supports this use case, so that was quite interesting. But I will come back to that later. So how can we use my library? Well, yeah. So given this proxy class, so what the proxy class does is as soon as data is accessed, it lazily loads it from disk. Those details are not really important. The important thing is that it mimics the interface of the underlying data. So how we can do this? Well, first of all, if we want to call a free function that to which we pass our proxy object, then we actually don't need to use my library because we can just implement this user-defined conversion function, which will be automatically called as soon as we pass a proxy to a free function. The problem you will get if you try to call a member function. So like this. So if you call proxy.begin, that won't work. And in order to make that work, we can inherit from the using class. And you should think of that, that the proxy class is using the public interface of the type that we are giving it. So for example, if we have a proxy of a vector, then it's using the interface of the vector. So it's mimicking the public interface. So we can now use the begin function. We can also use the operators. And another interesting function we can call is backinserter, because backinserter only works if the object that we're passing to it also has a nested type, and in this case the value type. So that means that our smart reference library also needs to expose the nested types, not only member functions. So basically what it does, if you inherit from this class, then it will automatically generate these types and functions into your class. Yeah, so now we support the standard library and other classes that conform to the interface with standard library, but we also want to support our own classes. That is also supported with a little help from the user by marking those identifiers as reflectable. The idea is that once we have proper reflection, that this is not necessary anymore, and then there is no manual intervention from the user necessary anymore. So by reflecting on the first name and last name, we now support those member functions as well. So how is this library designed? I want to discuss how member functions work, member types work similarly, and actually also free functions. So we start with defining this using class. It acts as a reusable base class. So from this class, you can create your own smart reference classes. So this is not a smart reference, it's the class, the derived class that becomes a smart reference. So for example, the proxy. So in order to give the proxy class a begin and an end function, what we can do is we define these two member functions in the using class, and then they simply delegate it to the derived class by first calling delegate. And then in the delegate function, we trigger a conversion to the underlying type, to the delegate type, in this case, the vector. And then in this using class, you see that this user-defined conversion function is also defined, but it's virtual. And that means that in the derived class, because it's also defined there, this implementation is used once we call the delegate object. So here we inherit from the using class. If we call delegate, then this, the logic of the smart reference class, in this case, lazily loading the data from disk, is called. And then in the end, it returns the data. And then if I go back, then here we have the underlying data, and then we just forward it to the begin function of the vector itself. So that works for vector, but we want to generically support any kind of class. So that's quite simple. We just templatize this class. However, then we have a problem because vector supports begin, but a unique pointer, for example, doesn't support begin. So we need to conditionally include the member functions, and we do that by using a trailing return type together with a trick called substitution failure is not an error. By making the return type basically the exact same expression as the body of this function. As soon as this expression fails, then compilation won't fail, but it will simply kick out this function. So it won't be available. So then your program still compiles for types that don't support the begin function. But in the previous slide, you saw that we were using virtual functions, and as we all know, virtual functions result in an indirection, and therefore this might become a bottleneck at some point. And in C++, we want to have zero overhead. That we can do by inheriting from the using class again, but in addition to specifying the underlying type, the delegate type, we also give the class itself. This is called the curiously recurring template pattern. So if we now look at the definition of the using class, it gets a second type, the CRTP, for that pattern. And then the delegate function does two things. First, it performs a downcast by casting to this CRTP type. And then it does the same as what it did before. It casts to the underlying delegate type. And then we have the delegate object, and then things were like they were before. And then the compiler can inline everything. So we have zero runtime overhead. And we also have zero memory overhead because there's no additional memory needed for this mechanism. If we want to support user-defined types, it won't work with this current setup because we want to make this mechanism extensible. So for that, we define this member class. which we define, which we specialize for every member function that we want to support. So for example, for begin, we specialize it and we give it an index. So let's say begin is the first function we want to support. Now, then we call that one 0. Yeah, and apart from that, everything is the same as the previous slide. And then the using class will inherit from all these member specializations. So for every member function that we want to support, we specialize a class for that, and then we inherit from all of them. And we use a macro to make this a little bit more tidy, because you don't want to repeat this for every member function that you want to support. So then, in the previous slide I showed that you can use reflectable first name. That's basically how this works. And the library itself supports the entire interface of the standard library using the exact same mechanism. So it just does reflectable begin, end, sort, whatever, such that the standard library is supported out of the box. So that was the design last year, and like I said, I've been continuously developing it, and there were some problems that I had to fix. So I came up with an alternative design, and as a side effect of that, it turned out that I could support another use case as well. So first of all, in the previous design, so if I go 2 slides back, you can see that in this member class, the member function, so let's say this is the begin function, this is actually the reflection layer, or the reflection emulation layer. And this layer should not be coupled to the smart reference layer. So what I did there is uncouple the delegation here from this reflection layer. So here you can see that in the begin function, instead of calling delegate, I perform a downcast to the derived object. And you can also see that we have a template parameter less, so we no longer have the delegate type, but only the CRTP type. So we perform this downcast to the derived class, so in this case that will be the proxy class, and then we call onCall, which we pass an invoker object. Well, what this invoker object does is, given some object, it's fully generic, we call the begin function on that, the member function. So if this is a vector, then it will simply delegate to this vector. Yeah. So in the using class, we can then define this onCall function. It receives the invoker object, and the implementation is very trivial. It calls this invoker and it passes the delegate object, because this this using class has access to the delegate object. It might seem a bit overcomplicated, but this allows you to perform additional logic in specific circumstances. So for example, the proxy class might want to do some additional logic compared to another proxy class, a smart reference class. So for example, the strong typedef might do something else. This actually allows you to prevent reference leaking, because now if you directly return what the invoker returns, so what did the invoker do? It redirects the call to the vector. So for example, vector.begin. What that returns, we can encapsulate it as well. So we can wrap that in some other object. The next slide will make clear why that is very powerful, because of the unified call syntax. So this already becomes a bit more complicated. So if we change the member class to give it a slightly more complicated invoker. In this case, we are composing two invokers. The first invoker is just like the previous slide. It calls on some object the member function, but we here also define a non-member syntax invoker, the invoker non-member, which calls this function using the non-member call syntax on this object. So it basically does it the other way around. And if we then create a class named composed invoker, which inherits from the first one, such that it does what it did before, and we give it a member function as non-member, which it's a bit complicated, but basically it returns a copy of the non-member invoker. Then we instantiate this new composed invoker, and we give it to the onCall function. What we then can do, we can create a class called unified call syntax, in which the onCall function receives this invoker object, which is the composed invoker. And then what it does first is it extracts the non-member call syntax version of this invoker. And then using this invoker, it will perform the actual call. First it extracts the delegate object, and then it calls this function, and then the result is wrapped again in the unified call syntax class, because we want to allow for chaining. For example, if you have a function that has as input a vector and as output a vector, then you would now, without wrapping, you would return a vector, and then you cannot chain the function calls anymore. You cannot do object dot and then something, because then after that something, it is a vector again, and then you cannot use the unified call syntax anymore. Now, I hope it will become a bit more clear in this example. So assume we have two functions defined, sort, unique, actually all those functions that we're using there, but I skipped them. Then we can create an alias, the dollar, for this unified call syntax class, because we want to make it a little bit more concise. Then we have our vector, and now we can wrap this vector inside this dollar, and then we can say dot sort, dot unique, dot filter, dot transform, and dot sum. And what it actually does under the hood, it will use the free function, so this non-member function. But as a developer, you can use the member function syntax. So to conclude, using this library, we can implement using current day C++. We can emulate smart references, which support generically the entire STL. And with a little help from the developer, we can also support user-defined types. And hopefully in the future, when we have proper reflection, we don't need this anymore. And it is also zero overhead, which we require for a facility like this. And finally, by using an uncoupled design, we can support many more use cases than what the smart reference library was actually designed for. So that opens up interesting use cases. So the library you can find on my GitHub site. And with that, I would like to finish. So thanks. Any questions?
Have you looked at all at what kind of error messages you get if you try to invoke a member function that isn't present on a type, and potentially what result an IDE gives you if you try to enumerate the possible functions you can use on a type? Does it correctly hide all the ones you're not going to get?
So if I understand correctly, your question is that if you have a type that does not support some member function and you still call this member function, what will happen in the compilation error message?
Yeah.
Well, it will basically say that this function is not found, just like if you use a normal class that has no member function, it will give the exact same error message.
I guess it's not like 10 pages of error.
And then that will be the first error message, and then it will give 10 or maybe more error messages. That will be one of the next things I will be working on. I have some ideas to really hide it, because for member functions, the lookup is done at the moment you try to use the function. So it doesn't actually, it's a very late lookup. So, I can do it differently, that while instantiating the smart reference class, that it already removes them, but then other use cases will not be possible. So, it's a bit balancing what we want. But yeah, I will experiment with this definitely, because it should also be usable for the developer, I agree.
Thank you.
This is quite an undertaking. You should be proud. You mentioned that this is zero overhead. Have you looked at the code gen for this? In light of some a talk earlier this week, Simon Brand's type wrappers talk, it seems like there's a lot of corner cases where this might be generating extra code. Have you looked into that at all?
I have not yet.
Okay. And secondly, I was wondering, does it currently support reflection on member function templates with non-deduced parameters? And if not, do you think that's something that's possible?
Yes, that works.
Wow, very cool.
Yeah, that was very tricky to implement, but it's supported. What is not supported is if you want to expose a member function template that has non-type parameters. And I have no idea how to support that at the moment.
So now that you've done all this work, do you still want language support for unified call syntax?
Yes, because I think some use cases are very hard to implement with this library. Currently, I'm working on supporting data members. I have some ideas how to support this also with zero overhead by using a union, which then will result in that we can overlap it with the memory in the derived class. Mm. But if you, for example, want to copy a data member of a class, in which case that data member is in which case that smart reference has a data member, then we get undefined behavior, because it will access, it needs access to the parent object containing this data member. So I think this is solvable using the proposal from Herb Sutter, in which we have, in which we can determine how the auto should be deduced.
Yeah. That's sort of the problem that I was thinking of.
I can emulate that, but not without zero runtime overhead. So, I think in the end we need a language facility.
This was very cool. Thank you. I'd like to subscribe to your newsletter.
Thanks.
Do I understand correctly that you kind of need to have a record for every possible function out there? Like that dollar syntax and then dot, and you can call sort, you can call any of the algorithms. So in your standard implementation, you need to know all of them with all possible parameters. That's how it...
The identifiers need to be reflectable. So if those names are not part of the standard library, because my library will give them out of the box, then you need to explicitly make them reflectable. So if you have your own functions defined, then you need to create one line per function.
Okay, so in other words, you don't need to follow up with code changes every time some compiler does something differently. You get it all automatically through mechanism of reflection, sounds like.
Yeah, it tries to emulate it. So yeah, hopefully this will be supported, and then you can remove those one-liners. Okay, thanks.